All right, greetings, fellow human, and welcome to a learning session for programming specifically. But this is really like a dive into what people call software engineering. So, what's the difference between programming and software engineering? I have reason to believe that software engineering encompasses a lot more than simply the raw code. Better question would be what's the difference between programming and coding? That's a question that we would have to find out another time. We're going to continue learning JavaScript. I have right in front of me the Eloquent JavaScript 4th edition by Martinst Haverbeke. That sounds to me a name that is probably from Scandinavia, if I had to guess. We will verify that in due time. But for now, this is a Creative Commons book. It's a really nice series of books. The ones with the birds, really nice series. I highly recommend. They seem to be, I think, made with a lot of care, delicacy, effort, creativity, and thoughtfulness. So this is why I'm going to use this book. It's also free. And so we're going to use it to better understand JavaScript. So right now, I've been trying to, for the last hour or so, simply just trying to like break apart the table of contents. Now, one thing that someone told me, I saw this in a YouTube video, that you don't need to know like all of a programming language, or you don't need to know like all the languages to be a programmer slash software engineer slash developer, etc. Because there's simply a plethora of information to know. You're not going to know it all. In fact, a lot of the work is about constantly learning and a continuous learning experience. Now, I think the thing that's most attractive about software engineering, and I want to break this video up into timestamps probably, but for the sake of editing, I probably won't. But understand that we're kind of going through different sort of chapters, if you will, with regards to different metas, different concepts with regards to how we think about building software or working with software. And I don't think it's purely software either. I think there's a very fundamental hardware component as well. But of course, you got to take an even step deeper into working with the hardware if you want to understand that. So my general approach when it comes to learning, I like to approach things in a systematic way. I think my ultimate goal is to understand systems engineering more so than software engineering, but they go hand in hand. And so I think a big part of understanding that is understanding the big picture and learning how to see the big picture. When I was younger, I talked to the women in my family about this concept called zoom in, and zoom out. Now they told it back to me. They were telling me like, "Wow, Diego, that's a profound concept. Zoom in, zoom out. Thank you very much for sharing this concept." But when they told it back to me, like what the concept was, for some reason I didn't really like see the importance of it. I didn't see the significance of it. But I'm coming back to it right now. And I think it's a very simple concept. It's a very intuitive approach. But it's the idea that if you're like looking through a magnifying glass, let's say we're like Galileo, right? And we're looking into the stars every night. Ideally, you have a tool that allows you to zoom in and zoom out. Maybe in the future, there will be some kind of handheld telescope that allows us to zoom in. I think nowadays there's cameras that allow you to zoom in on the moon and then zoom out. The idea being that you can see things at the smaller scale, see things at the bigger scale, and in the process recognize that both are equally important, but you're just seeing the whole process at different scales. And so it's a very fascinating concept. It's one that applies to many different aspects, but I think overall it applies to the 20th century, applies to the 19th century, probably applies to every century in human history. But, obviously with the industrial period, scale has been a big theme, production has been a big theme. And so it applies really well to the history of physics, especially because, you have Newton's equations, then eventually you had Maxwell's equations. These are talking about like everyday handheld objects, um, you know, all kinds of objects. But as physics evolved, we eventually dived into quantum mechanics, which actually focused on particular atoms. And then, you have general relativity, which existed in tandem with quantum mechanics, came a little bit before quantum mechanics was fully established. But basically, general relativity talks about the large scale of the universe. And in the years that followed, say 1940s, say like the post-nuclear bomb period, there was this big exploration in astronomy and even cosmology. And so gravity, the study of gravity, played a really large part in understanding how universes, not universes, but galaxies were formed. And I believe the quantum mechanics, and my audience can correct me if I'm wrong here, any physicists who are watching this video, but basically, they took a dive deeper into quantum mechanics, and then you end up into like basically some kind of atomic theory that talks about all these kinds of subatomic particles. And so this is a really the physics. I think it's the clearest analogy here of zooming in and zooming out. Right? You can study a galaxy and treat every star as a object, and then you can zoom in and then actually focus on the individual particles that make up that star. So that's kind of more or less the idea. So when it comes to learning software, I believe the approach here is to always introduce, these videos with some kind of large system understanding, bigger picture. And then as we start to learn more programming, and programming is kind of the main theme here, is to then dive deeper into the technical side of things, into the logic, the syntax, understand certain methods, understand the structure of the language, syntax and diction of the language, and then begin to figure out from there, start to combine both and figure out where's that going to take us. So when it comes to building, say, a website, you're going to start using multiple tools. You're not only using one language anymore, you're using multiple languages. You're understanding how servers work, you're understanding how a computer functions, you're understanding how the internet works, and you're understanding all these components that start to come together. And that's really the software's essence of software engineering. But I think for now, the focus is going to be really more on the big picture, which seems to be easier to understand. May not be more simple. There's a difference between simplicity and easy, and we're going to work on that theme quite a bit. But obviously, having a systematic approach may be simply more on the storytelling side of things. It's more like the folklore side of historical data, if you will. You don't need to know all the details. You just need to know generally, what continent, roughly what time period, and so forth. But then, of course, when on the programming side, it's very, very, very tactical, super tactical, all these kinds of details to work on. So that's my systems introduction. Now we can actually dive into this actual book. And so my approach, and this is, of course, these video series is all about basically how I'm learning to become a software engineer, with the idea that anyone out there who's learning how to software engineer that has a different style, you can use my style and you can grab bits and pieces, whatever you want, and just go ahead and use that for your own sort of design, architectural way of thinking, basically. And the idea is to optimize it. I think there's always room for improvement, always room for optimization. That's engineering fundamentals. Doesn't matter what major you choose. The idea is you want to optimize your ability, become a great developer, become a great engineer, and then, see what you can build. So right now I have 4 tabs open, 1, 2, 3, 4. And we're going to go through the table of contents and just focus on this book. This book is on JavaScript, right? I'm going to have to take like a bit of a break here. I think this is a good moment to pause, and just take a breath with me. Maybe one more. And with that, we can kind of have a bit of a either a mental or nervous reset and allow us to move on to the next phase. So let's see, what's the timestamp here? I'm going to check. We are, I don't think this thing actually has a timestamp. Okay, we're about 10 minutes in. Excellent. All right, there's my 10-minute introduction. Very good. All right, so I'm not sure how long this video is going to be. I think the idea is it's a relatively decent length. You can kind of think of it like a lecture. I don't want these video series to be lecture-like. I would like there to be some kind of engagement from my audience. But I guess, sit back, enjoy, and think with me, like help me, think methodically. So, with that said, JavaScript. What is JavaScript? It's a programming language. It's used for predominantly, I believe, back end of building websites. And there's actually a variety of JavaScripts. There's Node.js, there's several other types, but Node.js is the one that we will focus on in the foreseeable future. So, anyways, my approach to understanding JavaScript, I've been taking courses, I got caught up in what's called tutorial hell. And it's like, it's useful. I think it's a very profound skill to learn the tactical nature of programming. But I find that something tells me it's not the most optimal way to learn in the long term. Maybe sooner or later, I have to get really good at something like leet code. I think I was able to do a few problems in Code Wars pretty well. I don't know what my level was. It was probably like level 1 or level 2. I may actually put those links to those websites, but the idea, that's kind of what we were sort of taught. If you want to get into the developer space, you want to master leet code so that you can ace interview questions, and when you ace interview questions, you will then get hired at a software engineering firm. Well, I have reason to believe that we can think bigger than that. And the idea is to understand that programming is obviously a great profession to have, career and so forth, but there's something more valuable than simply having a job. It's about a way of thinking. It's a way of learning how to approach the world in an architectural manner. And so I think some of the greatest men of our time, there's a reason why they all seem to have this strong background in software engineering, because it's a systematic way of thinking. It's a way to organize thought. And so this book actually has a really nice quote, which I will pull up. See if I'll find it. I have it here. It's on page 17. I'll put it down here on the bottom left. But here's the quote. And the quote says, "We think we are creating the system for our own purposes. We believe we are making it in our own image. But the computer is not really like us. It is a projection of a very slim part of ourselves, that portion devoted to logic, order, rule, and clarity." And so it's basically a way of organizing our thoughts in a logical manner, and that's practical thoughts. That's the only way of thinking that we really need to have as human beings, is practical thoughts. And so being logical has its merits in that sense. So now what I wanted to do was to kind of go through the entire table of contents. That's kind of what I've been doing for the last hour, just trying to understand, try to dissect, try to see if I can digest more or less what the language is structured as. And I think the language is pretty universal. You've got values, which to me are simply variables, types of variables, operators, your basic calculator, not even a TI, Texas Instrument calculator, just a standard calculator that you would get from like middle school in the United States or elementary school even. Then you have program structure, talking about just basic things of the program. They finally introduced functions. Functions are definitely much more like cornerstone parts of the language. This is the bridge to the world of mathematics. Mathematics is fueled by functions, and so is computer science to a degree. So are programming languages to a degree, but functions aren't the only thing being used. You also have other things like objects and arrays. Those are actual data structures. But you also have methods. To me, methods are basically functions, as far as I know. And then the book dives into, so basically chapters 1 through 4 kind of give you a layout of like all the basic tools used in the language itself. Chapter 5, this is where things start to get a bit more expansive. We're talking about higher order functions, which is a certain type of function. It's a more advanced form of a function. They dive deeper into objects and the nature of objects. This book, the way it's structured, is very magical. So it's not really like a linear way of learning. It's what I've accepted. We have a project called a robot. And then chapter 8, I think this is probably the most interesting chapter that I've encountered so far in looking at the book, bugs and errors. And so I feel like when you're working with debugging, which I know that in the world of C++ is like the cornerstone part of C++. It's what makes people who understand C++ so good at what they do, because they are probably the best debuggers out there. And so, effectively, what is debugging? I mean, the story of debugging is a fascinating story. But there was a literal bug in the computer, and these computers were like massive machines that took up entire rooms, and they were all algorithmic. But the idea is that when you're debugging, you're basically finding the error of the program, right? The program is literally the whole packaged command that you're feeding the computer so that the computer does a certain action or a set of actions in the mathematical sense, a set of actions, each action being an element of that set. But effectively, that's interesting, isn't it? That's kind of some food for thought there, huh? A few more breaths here. Debugging is what we're talking about. It's the way to make sure that the program works, because you can create the program, do everything you thought you did right, and then test the machine. This is basically engineering 101. You build a prototype, you've tested to see if it will work, see if it flies, and if it doesn't fly and it crashes, it means that literally the design was flawed. You have to go back to the drawing board and design again. And so debugging is the process of finding the logical error. There's actually a variety of errors that go into the program. So let's dive into debugging. This is what I want to sort of dedicate to in this video. Let's see where we are on the timestamp. Okay, we're about 16 minutes in. This is what I'm going to read. Chapter 8, Bugs and Errors. Flaws in computer programs are usually called bugs. It makes programmers feel good to imagine them as little things that just happen to crawl into our work. In reality, of course, we put them there ourselves. If a program is crystallized thought, now this is a really interesting kind of like philosophical approach to understanding the nature of what programming really is. But it said the author says, if a program is a crystallized thought, we can roughly categorize bugs into those caused by the thoughts being confused and those caused by mistakes introduced. Excuse me. Oh my gosh. All right. If a program is crystallized thought, we can roughly categorize bugs into those caused by the thoughts being confused and those caused by mistakes introduced while converting a thought to code. The former type is generally harder to diagnose and fix than the latter. First time I read this, I didn't even realize that they were talking about two different things, right? Because they should have put like, this is me being a modder, modding, but it's like, first of all, if you look at the sentence structure, yes, there are two statements being said here. I guess it would be objects in our sentence. We can roughly categorize bugs into those caused by, one, the thoughts being confused, and two, those caused by mistakes introduced while converting a thought to code. So, all right, so I was going to put, this popped up. Okay, so I didn't even realize they were talking about two different things here, two different thoughts, and this is why I read it again, and then I realized that it still doesn't make sense, because it said the first statement they have here, which is like the I believe is the preposition, says if a program is crystallized, if a program is crystallized thought. In other words, if the entire program is thought, this is why I'm going to add a comment or pull up something like some kind of note sheet that like allows us to kind of dive into this a little bit more. So let's see, sticky notes. Let's try sticky notes. Oh gosh, I think I have to. All right, here we go. Sticky notes. All right, here we go. I'm trying to get this freaking piece of paper organized. All right. So, first statement they say is a program equals crystallized thought. Okay, that's the first thing that they're saying. Program is thought. Period. Got it. Facts. next statement they say, we can roughly categorize bugs into those caused by the thoughts being confused and those caused by mistakes introduced while converting a thought to code. So they're saying we can roughly categorize bugs into those caused by two types of thoughts. We can roughly categorize bugs into two types. They're trying to say that there's two types of bugs. I'm trying to translate what they're saying. Types of bugs. Something else to note is that some of the most brilliant minds out there may not necessarily be the best teachers, the best. I don't want to use the word educators, but the idea is that not necessarily the brightest minds are the best at teaching, or a better way to put it is not necessarily the most intelligent people are the smartest people, right? There is a type of smart which stands for SMART. What does that stand for? It's like super, mega, artistic slash perhaps autistic, ready, super, mega, artistic, ready, talent. There you go. That's what SMART stands for, okay? Which is different from being intelligent. And so this book, I have reason to believe, my spidey senses are telling me that this book is a very insightful book written by a very intelligent person. They understand JavaScript really well. They've written a very elegant book. It's literally called Eloquent JavaScript. They have a beautiful cover of a cool bird. This is a good book. And they even made it Creative Commons, meaning that they wanted to teach. They have a passion in teaching, and that's always a good sign. Having said that, they may not articulate all their ideas very clearly in a language that may be understood at a more universal level. And so I think a lot of the work that I'm dedicating to is to translate, to sort of be the middleman between, say, your layman business guy and, say, your programmer, and realize that they actually both are one and the same, effectively, and you want to be able to communicate to both really well. And so once again, some of the brightest minds of our time do this very well. They do a good job of working in a systematic, technical way, but they also understand that human beings communicate in very many different styles, and there's different ways of communicating ideas. And so the idea is to sort of merge both and realize that you can create an even more universal way of understanding things. And I think this is perhaps the very potential future for the science and technology age of humanity, as far as I know. Because this age isn't going away anytime soon, it doesn't seem like. And so there will be another generation of languages and tools that are being used. And take, for example, the leap from Web 2.0 to Web 3.0. That's a good example. Now, how are we doing on time? We are at the 23-minute mark. Okay, I probably should take notes just to keep track of time, so I can do the timestamps after the video. And did I lose my old notes? Oh gosh, I think I lost the old sticky notes. Oh, here it is. It's way down here for some reason. I have all these extra ones. We don't need so many. Can we delete these? Delete. Yes, thank you. Don't need it. Delete, and then one more. We're gonna delete this one too. And then I will have some personal notes on the bottom, just timestamps, so you can see my timestamps. 10-minute mark. We kind of jump into, so we had a systems approach. Then I would say it's more about table of contents. I think now the 16-minute mark was another transition. And then we're at the 23-minute mark now. And now we're trying to continue figuring out this particular statement here. Something like this. All right, so anyways, there are two types of bugs is what they're telling us. Two types of bugs, okay? The first one, what's the first one? The first bug here is those caused by, I'm trying to show you why this still doesn't make sense. Those caused by the thoughts being confused. And then the second one is those caused by mistakes introduced while converting a thought to code. Okay, so let's look at the first one. Those caused by the thoughts being confused. What does that mean? The bugs caused by the thoughts being confused. So what is a confused thought? I mean, what is a confused thought? That's a great question. I would say a confused thought is a illogical thought. That's my best interpretation. It has poor logic. It has poor logic, or perhaps better yet, poor rationale, if such a thing can make sense as far as a thought and perhaps even a programming language. It's a great question to know what is the rational nature of a programming language outside of the logic, because rationality taught by Rob Bensinger, you can check out my other videos on that, it's the idea that we can understand, we can use the structure of logic to arrive at a certain objective based on evidence, truth, etc., right? Based on some Boolean system. There's a thunderstorm going on right now, which is amazing. So there's that. Second, so that's my interpretation. Those caused by thoughts being confused. Confused, what does that mean? It means illogical or perhaps irrational. Right? Irrational would be the kind of the more umbrella concept here. Not purely, it may be perfectly logical, right? I mean, if you work with some of the AI models, they are logical in the way that they are able to arrive at answers based on the machine learning. It is 100% logical, but it may not be a rational response. All right. Number two, those caused by mistakes introduced while converting a thought to code. I think we have to take at least one more breath right now. One more. All right. Let's continue. Number two, those caused by mistakes introduced while converting a thought to code. Those caused by mistakes introduced while converting a thought to code. So in other words, there's some kind of translation problem here. Again, I would say that this may be logical thought, but it could be irrational, or what likely is syntax problem or diction problem. It's not really clear to us what they mean by. I mean, there's a lot of things that can happen. You know, it's like almost like it's like translating a language. You could take, for example, like, you know, you could have a designer. You know, it's like, I feel like the best analogy here is the relationship between an architect and a civil engineer. An architect is focused on the kind of artistic expression of the building. Yet architects, I think almost all of them have a foundation in civil engineering, at least in some fundamental way. They understand the kind of inherent nature of materials and structure and objects and so forth, and they understand like some sort of mathematical aspect as well. And so some of the most beautiful architectures of our time, of our era today, have deep mathematical like understandings, and they express them in very clear ways. So that's what architects focus on. They seem to have design which has elements that are mathematical in nature, but they're not purely mathematical, I don't think. I think I never went to architectural school, but my understanding is that, you know, the designing, and you see this with mechanical engineers when they're designing cars, for example. You know, when they design a car, I mean, they're focusing on the curvature, but the way they start to draw the figure, they first kind of create this sort of like grid. They first kind of create a grid, and then based on the grid, they focus on the design of the vehicle. So there's definitely this really design. It's like a really clever, efficient way of expressing art, of drawing. And it's a very technical method is what I'm trying to get at. So that's what architectures do. On the other hand, you have civil engineers. And what do civil engineers do? Civil engineers understand the cement. They know how to mix the cement. They understand the structural stability. They're working on things like strength of materials. They understand all the different forces that are working on the structure of an object. right? So you've got like all these different shapes and structures, joints, so forth. And that's what a civil engineer focuses on. So, as far as I know, this statement, those caused by mistakes introduced while converting a thought to code, I feel like there may be some sort of disconnection between the thoughtist, which would be the architect, and say the civil engineer, which would be the programmer. And there seems to be some kind of disconnection in the translation of the design to the actual programming syntax, to the actual program, rather. There's some sort of issue there, some sort of gap, barrier, something like this. And so I believe that's what they're getting at. And that's why I say it may be a logical thought, right? The design may be excellent, but it may not actually translate well into the actual forces of nature, which is what a civil engineer would focus on. A really good example of a vehicle in this case would be mechs, mech machines, right? And I'm right now operating without the internet, but if we were to look up, I might post some pictures of some really cool mechs in my post in the YouTube when I post this video. But like, if you look at mech design, they're some of the most amazing designs ever built. But there's a reason why they don't exist today, and it's because the gravity of these machines is not easy to do. Now, materials are changing quite a bit, and so it's very possible in the 21st century we do see more mechs. But like, I think the best example here would be the steampunk mechs. Like, why didn't World War One have really cool mechs? Instead, we had tanks. And a lot of it has to do with the forces of nature, specifically, the physics, the mechanics, mechanical engineering, so on and so forth. Big shout out to Mechanicus, by the way. So, with all that said, I think now we can take a pause here and take 2 more deep breaths. All right, let's go. All right. So the problem I have with this is that I have reason to believe that both statements could effectively be the same bug. They could essentially be, it's very possible that they're the same bug, but I think I've been able to add some clarity and make the point that they may not be. Right? There's more going on in the second statement than the first statement. I think the second statement is more general. The first statement, though, is clearly focus on logic and rationality. The second statement could focus more on things like syntax, right? Which has nothing to do with logic, I don't think. Well, I mean, syntax is all about logic, but I think it may be more of like a design implementation idea. And you see this a lot. I've had this issue quite a bit when I've tried to use HTML, CSS, and JavaScript. Is like creating very simple things like, a chessboard, for example. Like you gotta use a method as entirely different than the logic actually used when playing the game itself. And so I do wonder what a carpenter, like, how do they approach building a chessboard? And I wonder if that may be another method to understanding the nature of a game like chess, which has all these different elements to explore. All right, so that's the introduction of bugs and errors. So let's keep reading. How are we doing on time? We're at the 33-minute mark, 33:40. I think I wonder if I should stop the video here. Do let me know if I should continue a video like this or should I stop it here? Because we've just scratched the surface. I mean, we literally only read one paragraph of this book, of one chapter. It was this one over here. And it was profoundly insightful, but there's obviously a lot more that goes into understanding the language. We haven't really dived into the language yet. We've kind of focused more on sort of like the inherent kind of generalized nature of the language, right? So it's kind of like approaching mathematics in a general fashion and similar to this analogy. But obviously there's a lot more to go into when it comes to debugging. So let's see. I think what I'll do is like I'm just kind of skimming through the chapter. To see if anything sort of stands out. But I don't think anything really will. So I think I will stop the video here. I encourage you to check out chapter 8 of this book. Again, the book is Eloquent JavaScript 4th edition, Marinj Haverbeck. And I think this is kind of like, I'm going to kind of leave it for homework essentially. So yeah, that's a shout out to the academic world for sure. I really do think the wisest thing to do is to work with someone, but I think what we'll do is I'll leave it up to you to read the book yourself and do a little bit of research yourself. I'm going to do the same, and then we'll come together again in the next video and see if we've been able to make any progress. And I think in this way we'll spend as much time as we need on this chapter before we actually move on. I think that's the general approach. Thank you for watching. Like and subscribe. I'll see you in the next video. Peace out.